side scatter to acquire the leukocytes, and from the leukocytes, based on the CD14 marker, CD16 marker, differentiate the monocytes and the neutrophils. So this is something a standard flow cytometry does on a daily basis very easily. So ImageStream gives you the same kind of data, but the interesting part starts when you get the populations you are not supposed to see. So for example, something like here, it's not really usual that the cells would be even CD14 and also CD16 positive, double positive. So we are not really expecting this kind of population, or something like this. So there is actually nothing more easy than just to does it work? Maybe I need to click on it. Yes. Okay. So monocytes, neutrophils, and those are the populations I spoke about. So you can actually see that our double positives are actually the doublets we weren't able to get out during our basic gating. So you can actually see that the monocyte is stuck to the neutrophil. So this is something we are not that interested in. Or maybe we are. Actually with the ImageStream it's possible to do the doublet analysis. There are the immunologic sites where they are looking, for example, on the immune interactions between the T cells and the B cells. And here you can actually gate specifically on the doublets and observe the changes, the biological changes, for example, in the T cell. One of the applications would be the migration of the adhesion compound of the T cell from the cytoplasm to the place of the immune synapse. Right. So what I wanted to show you here is that you can be very confident in what is your sample, what are the cells of your interest, and what are just artifacts which need to be eliminated from your analysis. This can be very useful, especially if you are starting a new experiment. If you are not following just a protocol which has been established 10 years ago, but you are trying a new cell line, you are trying a new staining, you are trying a new permeabilization method, then you really cannot say if it works and if the staining is nicely specific on the surface or if it unspecifically stains your cell. Here you just display the cell, have a fast view, you can tell from the beginning, yes, those are the cells I want to use, or no, my new antibody doesn't work, I need to return it and buy it from somebody else. So this is what is meant by an excellent protocol development tool, especially if you are looking for something new, it can be a great helper. My second part of the application would be something which a flow cytometry does on the daily basis. I'll show you how the ImageStream can do not only the similar or the same data, equal data, but we can get on top of that a couple of more information. So cell cycle in the PHP1 cell line, and as a standard flow cytometry, even a ANMIS gives you the very typical histogram based on the intensity of DAPI. DAPI nuclear staining, the overall intensity is translated to the overall DNA content. So our cell line would have the G1 phase, cells in G1 phase, cells in the S phase, and cells in the G2 and N phase. This analysis was done using the FlowJo on top of the data acquired here, but with the percentage. So this is something the standard cytometry will give you as well. However, we can look a little bit deeper into our cell line, look at the texture of the DNA staining, and based on the high texture differences, differentiate the G2 phase and M phase, the mitosis phase, and identify and statistically express at different stages of mitosis, like prophase, metaphase, anaphase, and telophase. Here, always in comparison with the white light microscopy image, you can see that the cell is already divided. So this is something you can't get from a standard flow cytometer. But the reason why people usually buy and use ImageStream in the first place is to combine a standard flow cytometry experiment with something more, with looking into the actual biology of the cells. So applications like cell signaling, internalization and phagocytosis, surface intracellular colocalization, immunologies, especially cell-to-cell interaction. Okay, so cycle and mitosis, we have just seen that. There is a couple of genetical applications like fluorescence in situ hybridization. It's possible to look on the thread applications, or some people use it for oceanography. They look at the morphological differences between the microflora in the coastal waters, and based on this they do the identification of the specific subtypes of the microflora, and based on that they assess the quality of the coastal water. So there is really many applications. Let me show you one based on which I will try to show you how the instrument works and how it nicely combines the standard flow cytometry application with something a little more. We will look at the cell signaling. But before I will go there from the point of view of the flow cytometer, let me look at the same issue. I'm sorry, something wrong. Okay. In this experiment, we do have the monocytes. Isolated monocytes, and they are incomplete stimulated by lipopolysaccharide, a particle from the bacteria cell wall which is inducing immune response in the monocytes. This bacteria cell wall particle, this lipopolysaccharide, would induce immune response, which would be shown as a translocation of nuclear factor kappa B, from the area of the cytoplasm into the nucleus to start the producing some immune particles and so on. So this is a sample of the incomplete nuclear factor kappa B translocation, and this is basically what you would get under the fluorescent microscope. And now, could you tell if this sample is more translocated or more untranslocated? How would you even objectively assess such an issue? You would say, okay, this sample is, these cells are untranslocated, so it's untranslocated. Or somebody else can come and say, this and this is translocated, the nuclear factor kappa B is in the nucleus, so who is right? So that's what the image-based features of this system do, is that they, I'm sorry, they compare the intensities in each pixel of the cell, and they are looking at the nucleus, and they are asking, is in the nucleus the high intensity of the nuclear staining? Well, usually it is. But is there at the same time in the same pixel, over about 500 pixels per cell, so is in the same pixel also the high intensity of the nuclear factor kappa B staining? If yes, it results in a high similarity score. If no, it results in the negative similarity score. And you get such a profile, such a, let's say, histogram, but not based on just intensity, but on the comparison of intensities, in this case called similarity, an image-based feature. In this kind of experiment, it's very important to have a negative biological control to observe how this profile shifts from completely untranslocated to translocated images. Let me show you how this thing was measured on the image stream X. But this time, to be a little bit more difficult, this was not an isolated monocyte. This was the whole blood, which was incubated in liquid polysaccharide. First step to identify a different white blood cell types was the immunophenotypization. So each one white blood cell type of the interest, in this case it was neutrophils, monocytes, and the T cells from the lymphocytes. So they were immunophenotypically stained. So we have the four-color immunophenotypization, and the staining was also done for the nuclear factor kappa B and for all the nuclei. It was collected 20,000 cells at the 60x magnification on image stream. And they were trying to quantify the nuclear localization in the whole blood substance, in those different types. So this immunophenotypization was done on CD14, CD45, CD16, and CD3. So monocytes, CD45 are lymphocytes T cells, and CD16 neutrophils. So, based on this, different white blood cell types were identified. So neutrophils, first you can see a very nice typical nuclei shapes, but of course they were gated based on the CD16 expression. The eosinophils have the furthest, highest site scatter granularity. Monocytes are CD14 positive and a little bit CD45. However, the T cells would be very high on CD45 and also positive for CD3 marker. So the different cell types were gated. And based on those gates, based on those populations, they were looking into the cell signaling in each of them. They were looking in each of those types whether the nuclear factor kappa B will translocate from the cytoplasm into the nucleus after stimulation with lipid polysaccharide. So they have the negative control with the untreated cells, where you can see that the similarity scores are mainly around 0 or negative, so not really a big translocation happening, neither in monocytes, neutrophils, nor T cells. However, after stimulation with lipopolysaccharide, you can see that the monocytes in yellow specifically responded in comparison with the neutrophils and T cells who didn't react on such a stimulus. So the question is, could you do such an experiment with the standard flow cytometry? Not really, because you would get up to the point that you would identify a different cell populations, but the overall DNA content is the same. The overall content of nuclear factor kappa B also doesn't change, just the localization. Doesn't work. Okay. So this was one of their pilot applications they started in stream with, but by far this is not the only one. There has been done a whole bunch of experiments. I have here another. For the time reasons, I will go just very quickly through it. This is the experiment with the plasmacytoid dendritic cells, very rare cell subtype. Now they linked with the production of the antiviral interferon alpha and so on. But in this case, they would look on the